So I see you got your slide up, and I'll let you talk more about what you're doing in this area.
All right, thank you, Dr. Katz. So we are the autonomous photography drone. And as I mentioned, William and I are here today to present this. And one of our advisors, Dr. Adebege, is also here. So our goal for this project was to create an autonomous drone that can capture photographs of properties. And it will do this by navigating between multiple GPS location points and include an interface that can switch operating modes between manual and autonomous and vice versa. And it'll be capable of taking pictures autonomously and store the images on board. So the direction we chose to take with this project was we inherited a previous legacy project's drone frame, as well as their Raspberry Pi and Navio 2 flight controller, and a Python skeleton code to build off of. We want to have manual operation and altitude control for the drone, which we already have done. And we created a MATLAB Simulink block diagram to test the control system. And we also created a Gimbal Rig testing mechanism for tuning the drone values. And we will be currently working on the autonomous operation portion that includes the camera. So here's a list of all the electrical hardware for the drone itself. And as you can see listed here, we have our frame, motors, propellers, and etc., all for the drone itself. Going into a little more about the photography aspect, the picture in the top right is our camera, and it interfaced directly with the Pi, and it'll be mounted to the bottom of the drone. And we will use this to capture photos autonomously and store it on a onboard SD card on the Pi. Here's a block diagram of our drone. So this is for the manual flight. As you can see on the left, they have their controller and the transmitter, which corresponds to a receiver and a Navio on the Pi. And then that all leads into our speed controllers on the wings, which feed into our propellers and the motor. And obviously the battery powers everything, which is a LiPo battery. Getting a little bit into the surface level control theory, we had to implement a control system to tune the PID values of the drone. And an understanding of this implementation was needed to implement it in both in Simulink and to understand it in actuality. So the 12 equations on the right is what we mainly based our project off of in terms of understanding the control. And the citation for that is on the bottom. So going into some thrust measurements we did for our propellers and motors, it was crucial to test the motors to make sure that we could allow our drone to fly. Since we're using a quad rotor, we have 4 motors and propellers. So the thrusts were tested at various throttles for each motor with a 22.2 volt battery. And the ideal thrust to weight ratio for quadcopters is 2:1. And the weight of our drone is a little over 4 pounds. So our ideal ratio can be obtained at throttles less than 50%, which is ideal for not running the motors too hard because they do get very hot. And our thrust measurements are on the right there in that table. So I'll hand it off over to Billy.
Yeah, so as Alex mentioned before, we have designed a gimbal testing stand, which will allow us to tune the motors of our drone in the yaw, pitch, and roll axes. And this will just allow for smoother flight. And it's also ensures personal safety of the user because we won't have the drone flying in any direction we don't want, or it won't be crashing and whatnot. So that'll allow us to fine tune anything we need to take a closer look at. So here's our take on the design. As you can see, we have a bar through the center and 2 other rings on the outside. So this will allow us to move in the roll, pitch, and yaw axes. And as for actually constructing it, these are some of the components we already have. As you can see on the left side, we have 2 parts of the rings. And on the right side, we have the connectors that'll be housing our bearings and shafts to allow it to rotate. And we can safely say that at this point, the gimbal rig is about 85% completion, and we anticipate it to be completed very soon. And as for our Simulink control system diagram, from our research, we were able to develop a block diagram that'll allow us to determine PID values using our program and allow us to get some tuning values using our simulation.
Okay, and I think you need to move on a little bit.
So in terms of our Navio 2, it has the capability of running an open source program called ArduPilot, which essentially allows us to have like a base station to control our drone remotely. And it's going to help us with our point-to-point navigation method for our drone. So now we have a video of some of our tests. And moving forward, the big challenge of the semester is the point-to-point navigation. And in order to achieve this, we need to have our real-time GPS sensing and checking completed. And we also have to implement the pitch, roll, and yaw axes for the X and Y axis navigation, which we'll be able to achieve using our gimbal rig, and other additional tasks that are not that can be completed at any time are the camera mounting and the autonomous photography portion of it. So now we'll take a second, see if you have any questions.
We don't have a lot of time for questions. I think we take one question, we move on the schedule here, but we can pick these up at the end if there's extra time at the end of the period. So you guys did a very nice job. Any questions? Well, I'm going to hold mine and let our next group set up.
All right. Thank you, everyone.
Thank you.